Thanks, Lance. Thanks to the organizers for this very stimulating and interesting conference. Yesterday you heard a beautiful talk from Will about what happens if you put 6,000 pions in a 6 centimeter cubed box, which turns out to be essentially infinite volume in that case, and you learn about finite isospin density. Today I have a much less ambitious goal. I'm going to tell you what happens when you put 2 or 3 pions in a similar sized box. And the difference is that whereas Will, through various black magic, managed to get the energy levels, the lowest energy for each number of pions, in this work we're going to get 30, 40 different energy levels, not only the lowest one, but many excited levels. And from that information, I hope to convince you we can extract scattering amplitudes. So you can think of this as you have 2 or 3 pions, or it doesn't have to be pions, particles moving around in a box. Most of the time they're almost free. They interact a little bit. That shifts the energies from the free energies. And the information about scattering is contained in those energy shifts if you know how to get it out. So in this way, we're able to do something which is impossible experimentally, which is scatter 3 particles off 3 particles and get their scattering amplitudes. As I'll show you, in the case of 3 pions or 3 kaons, we can do that with physical quark masses now. Now, why do you care about that? Well, I'll tell you, this is my outline. I'm going to begin by trying to explain why this is relevant to many of you in this meeting. I'll give a brief overview of where things stand in pictures, so that can be your takeaway. And then I'll tell you how you do this, how you determine scattering amplitudes, infinite volume quantities from finite volume lattice QCD. And I'll give you, if I have time, examples of applications, recent things that, these are very biased, these are things that I've worked on, 3 particle amplitudes involving maximal isospin pions and kaons at physical quark masses, and then studying dd pi scattering, which is relevant for the recently discovered doubly charmed tetraquark. Okay, so here's one reason why you should care about this. If you can determine 3 to 3 scattering amplitudes, then you can determine the properties of resonances from first principles. And now we know there are many resonances. Some of them are fairly simple, like the rho and the omega, but we now know over the last few years, last decade, there are many more resonances that have been discovered at CERN. You know, there's some fairly conventional ones, excited Ds. There are these X and Ys and Zs, which are less well understood. There's the doubly charmed tetraquark, there's pentaquarks. There's a lot more structure in the resonance spectrum than perhaps we expected, and this is telling us about how the strong interactions work, is telling us about how confinement works. So we want to be able to do this. We want to be able to start with QCD and make predictions which are relevant for these particles. Another reason that I'm interested in 3 particles, particularly, is that as we heard a little bit indirectly from Will yesterday, the properties of neutron stars depend upon multiparticle interactions. In particular, the 3-neutron interaction is very important for determining the softness of the equation of state of neutron stars and the properties of large nuclei, and we would like to be able to determine that from first principles. I have a third motivation, which I'm not going to really talk much about today, but in parallel with the developments I'm going to describe, where you calculate scattering amplitudes, you also develop the methods which allow you to determine decay amplitudes through electroweak physics. You know, for example, k to 2 pi, which is something essentially done, k to 3 pi, where we now know how to do this, and where we don't know how to do this are d decays. And why do we care about this? Because, for example, in d decays, CP violation has been measured. We don't know whether it's consistent with the standard model. So we want to be able to develop methods to figure that out. Okay, so with that, I'm going to just show you a few pictures to describe what the present status is. So In terms of two-particle scattering from lattice QCD, we are now in the situation for the lowest, simplest resonance, the rho. There are multiple results with physical quark masses, and fortunately, the result agrees with what we measure experimentally. So that's a benchmark that we are able to do that calculation. For things involving nucleons, it's a bit harder. We can get down to perhaps not physical quark masses, but close to it, and map out the delta resonance. As I already said, we're able to calculate the k to 2 pi amplitude, including the CP violating part, basically with all errors controlled. Let me just flash one result. This is for the delta, and what this shows on the right-hand side is the result of a fit to lattice data, and I'm not going to go into it, but these are energy levels in finite volume which have been measured, from which, by a fitting procedure I'll sketch, you can determine the p-wave nucleon-pion scattering phase shift and see a beautiful resonance, which is the delta, slightly above physical quark masses. So that's sort of an approximate state of the art there. Where are we now? The present frontier, the reason I'm talking about 3 pions in a box and not 4 pions is because I don't know how to do 4 pions, but we can do 3 pions. And I'll show you results later on, if I don't run out of time, for these two cases, which I'm involved in. And here we have, as I already mentioned, 3 light pseudo-Goldstone bosons, a maximal isospin scattering off each other at physical quark masses. And here's the case where we're studying the TCC, which decays to dd pi, with somewhat above physical quark masses. I should also mention that also at the frontier is what happens when you have 2 nucleons, where it's there's been a long-standing uncertainty about, is there a dineutron bound state at heavier than physical quark masses? Is the H dibaryon bound? That's another topic. I'm not going to get into it, but it's the frontier. Coming in the near future are cases where you study, for example, 3 pions at non-maximal isospin. So you can look, for example, at the omega resonance. There's already been first work on this. We understand in principle how to do this, but hasn't been pushed through in practice. Personally, I'm working on formalism, which is basically complete to understand the Roper resonance. The Roper is something which decays to both 2 and 3 particles. And we do understand in principle how to calculate the k to 3 pi amplitudes, all aspects of it. But that's a very involved lattice calculation, but the theory is there. So that is the situation. Now let me sketch for you the formalism, or the issue that we have to resolve with this formalism. So what do we do in lattice calculations? As Will talked about, and maybe others previously, one thing we can calculate very well are correlation functions. And here's a simple 2-point correlation function where we have the vacuum, which is in a box, and we have some operator which, say, creates 3 pions. We can have many such operators. We let it evolve in Euclidean time and space some distance. We destroy it. There's the vacuum again. We project onto certain total momenta, which of course are restricted by the box. And this quantity, which we calculate using good old-fashioned Euclidean Monte Carlo methods, is given by a spectral decomposition where we have overlap matrix elements and exponential decay tells us the energies. Now, that's easy to say in practice. In principle, in practice, what can one do? By picking many operators using state-of-the-art methods, you can typically determine for each choice of quantum numbers, and that means each total momentum, and then there are also irreps associated with the factor in a cubic box, typically 5 to 10 levels for each value of those quantum numbers. And you have a whole bunch of quantum numbers, so you often end up with 50 states. As you go up in energy, you determine them less well, but you can determine many. As I said before, you can calculate now in many cases with physical quark masses. It should be kept in mind that, of course, these results come with errors, statistical errors, systematic errors. I'm not going to talk much about those today, when we do our fits, we fully account for the statistical errors, but we're not yet fully accounting for systematic errors. That's what one ultimately has to do. Okay, but the most important point to take away is that these energies here, if one takes the continuum limit, are physical quantities, finite volume energies from QCD. Doesn't matter that we've got at them using Euclidean time, it's the energies in a box. They're good physical quantities. And really all we're doing is milking the information in those energies to the maximum point. Okay, so that's what we have. We can calculate finite volume energies. On the other hand, we want to calculate scattering amplitudes, which are infinite volume quantities. And so the question is how to relate these. And that question is, has nothing to do with the lattice. We've in principle taken the lattice spacing limit, spacing to 0. We've got these energies. It's just a finite volume quantum field theory problem. How do you relate these two quantities? And I'm not going to derive anything. I'm just going to tell you how it works. So in the two-particle case, this has been known for 40 years almost, starting with seminal work by Martin Lucia. Now, if you have the non-relativistic quantum mechanics system where you have particles interacting with potentials of finite range, and you put two particles in a cubic box, you surely could predict the energy levels. And the way you can do that is there's a determinantal equation in which appears K2, which is the infinite volume two-particle K-matrix, which is basically a way of parameterizing the phase shifts, and a quantity F2, which is a geometric function, completely known, that incorporates the fact that you're in a cubic box. And this determinant, the indices are the angular momentum in the center of mass of these two particles. And yeah, I guess I say all that down here. When you go to quantum field theory, when you go to potentials which don't have finite range, then this is not an exact equation, but it's exact up to corrections which are suppressed exponentially in the pion mass. And for typical m pi Ls of 4 or higher, this is percent level errors, which we are going to ignore throughout this. And this formalism is valid up to the first place where you can create more than two particles, which for 2 pions would be 4 pions. So you have some energy range. So if you knew K2, you could predict the spectrum. In reality, what we have is we determine the spectrum, and we want to determine from that K2, so we have to parameterize K2, for example, in effective range parameterization. Anyway, in some way, or if there's a resonance, you put a pole in there, you then fit the energy levels with respect to these parameters, you determine those parameters. And then once you've got K2, it's just an algebraic relation to get the scattering amplitude. So that's the logic of two particles. Now, this determinant runs in principle over all angular momenta. In order to fit the particles in a square box, you're going to need all angular momenta. What you have to do is assume that the interaction for higher angular momenta vanishes, and then the free high angular momenta stuff does its bit to force match the boundary conditions, and in effect, what that does is truncate this equation. And it's a finite equation, you can just solve it. So that is the situation with two particles. About a decade ago, my now ex-student Max Hansen and I generalized this to 3 particles. And the situation, the workflow, if you want, is like this. Here you imagine where you have results for the 3-particle spectrum and the 2-particle spectrum. And I'll consider a case where 2 and 3 particles don't mix, like pi. You have a quantization condition, the one we just talked about, for the 2-particle spectrum, and you have another quantization condition, a more complicated one, for the 3-particle spectrum. This involves a 3-particle K-matrix, which we call KDF3, where DF stands for divergence free. Think of it as a short distance 3-particle interaction, which is a smooth function, real, and you can parameterize it in a generalization of effective range parameter. Expansion. So you parameterize these, you plug into this, you fit the levels, you get the parameters, and then the second step in this case is much more complicated. To go from this short distance quantity KdF3 and K2 to M3, the 3 to 3 amplitudes, you need to solve integral equations. And that puts in the unitarity constraints due to final state and initial state interactions. Okay, so I'm not going to say much about this quantization condition. Again, it's valid up to exponentially suppressed corrections. It's valid up to the first inelastic threshold. It is valid for relativistic energies. This is a relativistic formalism. The matrix indices are larger because you have 3 particles, so you have an additional index which corresponds to the finite volume momentum of one of the particles. The formalism includes a cutoff in K, so that is truncated. The truncation over the L and M of the other 2 particles you have to do by hand. And this F3 that lives in this quantization condition has this more complicated form, which includes now 2 kinematic functions, F and G, in addition to the 2 particle interactions. So you can think of this as adding up all the effects of 2 to 2 interactions except for G, which corresponds to switching between pairs of 2 to 2 interactions. Yeah, I'm not going to go into it. We know what F and G are. We can explicitly write down this matrix. Just to say a word about the integral equations, I've just sketched what they are here. They're given, so M3 is given by symmetrization of a sum of 2 terms. One of the terms involves only 2 particle interactions and corresponds to 2 particles interacting in pairs back and forth. Again, this G is a known function. And the important point is these M2s are on shell, the way we do things. And this contains all the divergences which live in a 3-particle amplitude. And then the remaining part corresponds to the underlying 3 to 3 short distance KdF decorated by final state and initial state interactions in a way consistent with unitarity. And we know how to solve these equations. When we do so, we project onto total values of total angular momentum. Okay, well, I'm not going to go through this. This is just to say that over the years, this has been generalized to basically all 3-particle systems, including spin, non-degenerate, etc. We know how to do that. Okay, so I have 10 minutes, and I'm going to tell you 2 examples of results from this. The first one concerns predictions for physical masses for maximal isospin multi-meson scattering amplitudes. Now that workflow I showed you includes many steps. First you generate the configurations. Then you calculate the correlation functions with all these operators and fit to get the energy levels. Then you fit those energy levels with the quantization conditions, and then you solve the integral equations. So you have to get a larger collaboration to do this. And so in this collaboration of all these folks, Drew, Ben, Colin, and Sarah were the ones who did the correlation functions. Someone else had generated the lattices for us. It's the CLS ensembles from Europe. And then my student Zach, Fernando, and I solved the quantization conditions, and Fernando and Sebastian David solved the integral equations. But still, on a lattice scale, this is a pretty small collaboration. So what did we do? We studied these 4 systems. As I say, so these are not very interesting systems. Three pseudo-Goldstone bosons at maximal isospin are systems with weak repulsive interactions. There's no 3-particle resonances. There's no 2-particle resonances in subchannels. But it's a benchmark. Can we do this? Are we able to pull it out? We generalized what had been done before by using physical quark masses. We studied the overall JP of these 3 cases, including subchannel angular momenta up to 2. Here we have a nice thing that we can compare to chi-pt, so we get a reality check. We used these ensembles, coordinated lattice something. What is this? Forgotten. Anyway, it's a group of people in Europe who've created lattices with improved Wilson fermions. The finding the energy levels was done with the generalized eigenvalue problem methods. The key thing that we have is that we're now using this lattice here, which has just slightly less than physical pion masses. We have a trajectory as the pion gets heavier, the kaon gets a bit lighter, such that the trace of the quark mass matrix is constant. So that's one way of approaching the chiral limit. M pi L is okay. Previously, we've done this heavier lattices. Now we're doing the physical one. And just to show you some examples of the spectrum that we're calculating, here's results, our results for 2 pions. Along the x-axis are the different frames. 0 means rest frame, 1 means total momentum, 0, 0, 1 times 2 pi over L, etc. And then these are the different irreps of the cubic group that enter. And for each of these levels, the line is the non-interacting energy, the green is the shifted energy, the one we measure with the simulations, and the blue is the result of our fit, which I'll describe in a minute, to these levels. And we go up to the inelastic threshold. We don't include levels above that, but we can still take our fit and determine what we would predict, and in all cases it works above that for a while. So we think we know what we're doing in terms of fits. Here's 2 kaons. Here you can see a little more clearly that there's bigger shifts, and these shifts have a highly statistical significant, like 10 sigma. So we really have shifts. As you go to higher momenta, the errors get somewhat larger. It goes to higher energy, the errors get somewhat larger. And here's 3 particles. Again, you can see we have very significant shifts. So we have a lot of energy levels. All these energy levels that I'm showing are correlated because they come from the same lattice ensembles. So when we do fits, we have to include the full correlation matrix, which is why it takes a long time. So the fits to the spectra, we parameterize these. So we've done these fits. So we fit simultaneously 2 pi and 3 pi, 2k and 3k, and then for, say, kk pi, we also simultaneously fit the 2 subchannels. And you can see we're fitting up to of order 100 levels with of order 10 parameters. Chi-squared is okay, good in some cases, not so good in others, but not bad. And out of that, we then get the amplitudes by solving the integral equations or the algebraic relations, and I'm showing you a couple of results here. One of them, the dominant effect in shifting the energies of 3 particles in a box is due to the 2-to-2 interaction. There's a shift due to 2-to-2, that goes like 1 over the volume. There's a 3-to-3 shift, which goes like 1 over the volume squared. So the dominant thing we get out is the 2-to-2. We get it out better with 3 particles because there are 3 pairs. So what I'm showing you here are the results for the phase shift, which you can see is repulsive in all cases for pi plus pi plus, k plus k plus, pi plus k plus in the lowest and second lowest partial wave. These data points are not fit. They are just showing you what you would get if you use the leading order Lucia formula, ignoring higher L's, which takes each energy level to a point on this plot. And you can see it looks like data, but what we do is this global fit, which includes more waves and does not a fit to that. And our results are shown in red here and magenta and blue. And they're compared to the experiment, which is basically the results of a dispersive analysis of data. And what you can see is we have comparable errors and the results are consistent. So we're really able to do physical things here. The higher waves are all consistent with 0, but consistent also with experiments. So that's a cross-check. When you go to higher masses, these higher waves are non-zero. And that's what I'm showing here. This shows you the scattering length, the amplitude at 0 as a function of m pi squared. This is the physical point. These are our other 3 lattices. We can do a chi-pt fit to this. This is very good. And this allows us to determine low energy constants in the chiral Lagrangian to high position. Okay, but I've been talking about 3-to-3, so here are our results, some of our results for 3-to-3 amplitudes. This is projecting onto overall scalars. Picking a simple configuration, the 3 particles coming in are in an equilateral triangle, equal energy, the 3 going out, similarly, in which case the relative orientation doesn't matter. And what I'm showing you here is the square of the scattering amplitude in some units against the energy for 3 pions, pi pi k, kk pi, and kkk. And, okay, we solve these integral equations, we get these results. And, you know, that's really the end of the story. It's not terribly exciting, other than we can do it. But notice that this diverges at threshold because this physical process where two particles scatter, one particle goes for a long way, two particles scatter is present. And so this is expected. We see that pions are more weakly interacting than kaons, again expected. Okay, the final plot I want to show, this is the one that Ian showed for me this morning, shows the case of the 3 pion amplitude for the different quark masses. You can see it gets suppressed as you go down to the physical one. And what's important here is that we compare to next to leading order chi-pt, and you get good agreement of the physical masses, less good agreement as you go up. So we think we know what we're doing. Okay, so in the remaining 3 minutes, I'll probably push this a little bit. I just want to flash a few results of another application where we are moving towards studying, predicting the properties of the doubly charmed tetraquark, this guy, which decays experimentally into dd pi. We want to predict its properties directly from the lattice, and this is based on 2 papers, one where we set up the formalism, and the other where we are using other people's data to show that that formalism is ready to go. Okay, you may not know much about the tetraquark. So this is, a particle which has the quark composition CC U bar D bar. So it's definitely a tetraquark. It's definitely an exotic. And experimentally, it lies just below the dd star threshold, but above the dd pi threshold. So it decays to dd pi. So to really study the physical situation, you need a 3-body formalism, which is what we have developed. Up to now, lattice QCD calculations have used heavier than physical quarks, and in that case, it seems like the tetraquark lies below the dd star threshold. Well, for one, the most important thing is that for heavier than physical quarks, the d star becomes stable. It's no longer decays to d pi, and the picture looks like this. So this is how it decays, and it looks like you could study this with the 2-body finite volume formalism. And that's what people did. So this is one example from a few years ago using pion masses of 280. They used Lucia's formalism. That allows you to get the K matrix, which is basically the same as P cot delta. P is the relative momentum. Well, this is the inverse K matrix. And each energy level gave them a point like this, and they fit it to an effective range expansion. And if you remember your scattering theory, if that line intersects this line, then you have a bound state. If it intersects this line, you have a virtual bound state. And they had evidence for a virtual bound state. However, this formalism breaks down at this red line, which is where there's a cut, or in this case a pole, due to pion exchange in the U channel. The 2-particle formalism fails when you hit this point, because amongst other things, this delta actually becomes complex. So this curve must be wrong. It cannot follow this curve, this point. So we need some improved formalism, and this is true in various other cases, and various people have suggested improvements to the 2-particle quantization condition. We suggested an approach where we use the 3-particle quantization condition, partly because we know in the physical case it's a 3-particle decay. But the way we did this was we studied the 3-particle quantization condition, dd pi, but we get the d star by putting in an appropriate d pi p-wave interaction such that there's a d star pole below threshold. And then, so that we can do by hand, and we know basically experimentally what that should be. And that means that even though we have a 3-particle, we get out a 3-particle amplitude, we can analytically continue it below threshold, use LSC, and pick out d star d scattering. And do that when we solve the integral equations. And because we have this underlying diagram, we're including this U-channel pion exchange automatically. So, I might actually finish on time. this is my last contentful slide. It's sort of hard to explain so there is this lattice data out there which is at a fairly early stage. What we did was answer the question was, could we run it through our formalism and more or less reproduce the data points, and that's what we're able to do here. These different curves correspond to different d star d pi couplings, all in the range consistent with experiment. But in our approach, we get the real solution to this K-matrix, and you can see, well, you maybe can't see, but below the left-hand cut, it actually picks up an imaginary part, as it should. So this is the true form. It does not cross this line. There is no virtual bound state. What happens is the virtual bound state moves into the complex plane, and we can track it. So it's an example of what you could do if you had better data and you did a complete analysis. So we're all set to do that and working on getting better data. Okay, I've come to the end. So let me summarize by saying the two-particle sector is entering a precision phase. The frontier is 2 nucleons, and I haven't talked about it, but form factors of resonances. Three-particle sector is now made big strides. We can do there are several applications, including at physical masses. We're working on the TCC with lighter quark masses. We're working on, we being the lattice community, the case where 3 pions in I equals 2, in which case you can have rho pi in a subchannel. 3 pions at I equals 0, in which case you have omega. Interestingly, there you also have kk bar. That brings you into contact with the Westerminer-Witten term in chiral perturbation theory, so you enter some anomaly physics, and we're working on the ROPA. Ultimately, we want to go to more particles. Okay, I lied, there's another slide. And this is my dream, this is my long-term dream, which is, we know from experiment that there is CP violation in these decays. In fact, present indications indicate that it's dominantly in d to pi pi. Is that consistent with the standard model? Can we predict what that CP violation is from using lattice QCD, using first principles? The challenge there is that at the d energy, this final state of 2 pions, you put 2 pions in a box, the strong interactions will mix them with 4 pions, zeta eta, blah, blah, blah. And in order to disentangle this, you need a 4-particle formalism. We don't have it yet, but that's the plan. All right, thank you.
Thanks a lot, Steve, for a great talk. Maybe I start off with one question. You mentioned the rho and pi to rho, but the rho is actually above the 4 pion threshold. So to do precision rho, would you also need 4 pi states?
I mean, obviously the answer is yes. It seems like, if you look at the particle data book, you'll find that the coupling of the rho to 4 pions is very small. So up to now, people have ignored it. But yep, ultimately, good point. Reality check. Yeah.
I mean, there's something funny about the rho. If you think about the mu on g minus 2, maybe there's something a little bit off there.
Yeah. No, I agree. I mean, of course,
not very far off. But.
I didn't say it, but everything I've shown you today is in the isospin symmetric limit. Right. So no rho omega mixing. So, there's lots of bells and whistles to add to this. Yeah.
Some more questions. Igor.
Yeah, thanks a lot. If I understand correctly, the tetraquark BC U bar D bar is of interest, right? And people are not sure if it's exactly bound or not.
The one with B.
With B, yeah. Like BB U bar D bar, people predict it's completely bound.
Yes.
So can you study these things? Because then you have a heavier quark, much heavier quark. And
yes. So the people who have studied the BB case have used methods where they're basically expanding about a static quark or something like that. Mm-hmm. BD is in between. So people have used methods. Well, they treat them like non-relativistic quarks, and the C is right on the boundary for that. So in principle, yes. It's just a more complicated situation.
So for you, it's more complicated than doing d pi?
Well, I mean, for mostly what I'm doing is formalism fitting. I'm not doing the lattice calculations anymore. Mm-hmm. That's for young people. In principle, I mean, there's no barrier to doing that case. Mm-hmm. It's, you know, every calculation is a big investment, so you pick your poison.
Okay.
Maybe I missed the spot, but say about the also exotic stuff, you know, when you mentioned that there's quite a number of those, right? And it's kind of a question about sensitivity of the method, because when we're talking about something like molecular or whatever type of stuff where different kind of scales are involved, right, in certain sense, how well you're feeling in this area?
So yes, I mean, if it's molecular DD star, then they will get quite far away from each other. But yeah. I think that we are completely okay with that situation. I mean, that would not mess up this formalism, because we make no assumptions about that. The question is, how would you get out of a lattice calculation information about the structure?
Yeah, was they sensitive enough to see this, right?
Yeah, I mean, so I don't know is the real answer. But, you know, when we get close to, you know, ask me again. It's very much, I mean, you know, one thing you can do, is a very basic thing you can do is, once you have a state, you can look at overlaps of that state with different operators. And see, you know, relative overlaps sort of give you some information, it's qualitative. And then there are these various criteria, the Weinberg criteria and stuff, and you can study that. But okay, for me it's a bit premature, but it'll come.
To get 2 to 4 amplitude, do you have to consider 4 particle states in finite volume, or can you get like 3 to 3 and then by crossing analytically continue and get 2 to 4?
Yes, if you had an analytic form.
But your equations, do they allow for some kind of analytic continuation like this, or not?
No, I mean, not really, because we put in the right analytic structure in terms of S-wave unitarity. But, I mean, I haven't thought about it a lot, but my guess is that we don't have something which is properly crossing symmetric. So we would need more work to think about that. That's all I can say. It's you know, if we had a 4-particle formalism, then we could do it directly. But I mean, ultimately, you certainly need an analytic form. If you can match onto chiral perturbation theory, then you could do something. But for other situations, higher energies, we don't really have any theoretical grounding to write down a formalism. So I don't know. But good question.
Maybe one more quick question is, I remember hearing something about sort of alternative Lorentzian approach, like alternative to the Schluter formula. Could you comment on it?
Yeah, so you might say, you know, one way of phrasing this is, you know, we're doing 2 and then 3 and then struggling to do 4 and, you know, then we're going to give up. But, you know, once you get to high enough energy, obviously you need many more particles. And so you really need an inclusive approach. And as you intimate, that involves doing something which is essentially in Minkowski space. And there's a lot of effort in that direction, basically inclusive calculations, where you automatically sum over the full spectrum with some weight function. And the problem there is doing an analytic continuation of falling exponentials to a sum of oscillating exponentials. What people have played with are various sort of intermediate weights where you smear the correlation functions with certain functions which you can analytically continue, but they're not exactly what you want. And then you try and take limits. That's there's a fair number of people working on it. It's at a fairly early stage, but I think there's a lot of hope that will become a real quantitative method in due course. Good question.
Do you happen to know if the experimentalists can get out the size of the amplitude for the TC to go to DD star? Or is that, I mean, that's something you're extracting, but I'm wondering if it...
Yeah, I mean, I think you can, yes.
Okay.
Yeah, yeah. I mean, because various phenomenological papers with various models have really done direct comparisons.
Okay. Let's see.
So there is the approach, one author is here, and you can think of multi-particle states, or just go in some basis, I don't know, pick some basis for relevant moment, and just think of them as infinitely many one-particle states, right? And then you reduce everything to just a bunch of 2-to-2 amplitudes, but now with many flavors. Do you think it can be useful?
I don't know. We should talk about it. I don't know anything about it. Yeah, sounds interesting.
Okay, this guy. Are you going to talk about it? Okay.
Okay, look forward to it.
Any other questions? Yep.
Can you improve the chiral Lagrangian? Can you find the coefficients in the chiral Lagrangian to find the effective theory?
Improve it in what way, sorry?
Well, I mean, first of all, you can match to the chiral Lagrangian, but then there are unknown coefficients as you go up in the series. And can you calculate those coefficients in the chiral Lagrangian?
Well, you can fit your data to the chiral and determine those. I mean, there's one example I sort of flashed.
Right.
Yes.
Yeah.
You can up to, I mean, next to leading order, that I think works very well. I mean, in flag, there's some examples of that, for example.
Yeah. And this is an effective way to find the effective action.
Yes. Yeah, exactly.
Actually, maybe one last question. You only had about order 10 parameters in this 3 goes to 3 fit you did.
Yes.
Seems like a small number given the number of degrees of freedom in 3 goes to 3 is. Is it because you specialize to a particular configuration, or it's just
if you
do
do
an angular momentum analysis on subchannels?
So what we did is we wrote down all the Lorentz invariant forms for 3 to 3, and it did an expansion about threshold.
Okay.
And at a given order, you have a certain number of terms. It's just like, S and T with 2 to 2, but it's a generalization of that.
Because you're near threshold.
Yeah, so if you go to higher, then, all bets are off and you have to do some more modeling.
Yeah. Okay. Any more questions? Otherwise, let's thank Steve again for a great talk.